digital solutions for water distribution session. As I briefly explained earlier, this is the format for this session. We have got 5 presenters. They are talking about their current research, and we want to see how this may contribute to self-healing pipes, create more self-awareness in water distribution networks. So each presenter has got 10 minutes, and if there is time, we'll do one quick question or we'll leave Q&A to end. And in the second part, we have got experts in the topic area. They are going to provide feedback on the presentations and also their vision for asset management in the water sector, how they see things go in the next 5 years, next 10 years. So we'll start the presentation with the first presentation. This is a joint presentation by Dr. Milid Latifi and Ramiz. And currently they are both working on a project. This is a knowledge transfer partnership with a company. So Ramiz is the associate on that project, and then they identify that they need to improve their expertise in machine learning AI, so they funded a PhD studentship. So Ramiz is the PhD studentship working on that. So they are going to do their presentation together. Over to you.
Thank you everyone. Good morning. Thank you. Good morning. My name is Milid Latifi, and I'm a postdoc researcher at Center for Water Systems at the University of Exeter. I'm working on a knowledge transfer partnership between University of Exeter, Center for Water Systems, and a company called Data Techniques, which is based in Salford, Manchester. And I'm working on a project to develop a digital twin for soil pipe systems. And the part of the research that I'm going to showcase today is about experimental soil type interaction modeling and life asset monitoring. This is going to be a joint presentation between Ramiz and I. So I will cover a part of the whole presentation, and Ramiz will cover the remaining. Starting with objectives. Main objective of the whole project is to understand the soil pipe interaction in water distribution networks and simplifying the computational costs and reducing the computational costs of the soil pipe process understanding, and then move to live monitoring of the pipes in the network, and then predicting the assessing the health condition of the pipes and predicting the remaining lifetime of the assets. We started with experiments, and at the first part we did some experiments on soils, pipe material, pressurized pipes, buried pipes, and then long-term tests. We started with tests on soil. We did some experiments to understand different mechanical or geomechanical properties of the soil, like soil gradation, shear characteristics of the soil, Atterbury limits of the soil, porosity, and different mechanical behaviors of the soil. Then we did some experiments on the pipe material. Tensile test has been carried out, creep test has been done to know the Young's modulus of the pipe material, yield strength of the pipe, and also rupture strength of the pipe. Then we moved to pressurized pipe tests. 4 sensors has been installed on 4 cardinal points of the pipe, and each sensor is able to measure the strain on 2 directions, both hoop and axial, and it can effectively measure and monitor the deformation of the pipe in different directions at different points. The pipes were pressurized from inside, and the pressure increased until the pipes were failed or broken, and then the pipes were buried in soil, and different combinations of internal pressure and external load was applied on the pipe to see, until the pipe was failed, to see how the pipe behaves in when it faces with different combinations of the soils of the loads. And in all cases, the data, the deformation of the pipe, strains on the pipe were accurate. And some extra tests were done. The failed points of the pipe were cutted and put under an electronic microscope to see different failure modes on the pipe. Here we saw a ductile failure mode in pipe, in PVC pipe, and brittle failure mode in other parts, in other failures. And here I have a short movie showing how we did the experiments in the lab, in our lab in Center for Water Systems at University of Exeter. We did some experiments on the soil, and yeah, here we measured the Atterberg limits. Then we cut the pipe, we sealed pipes from both ends, deployed sensors on different points, strain gauges on the pipes, and then we set up a soil box, and then we pressurized the pipes until the pipes were broken. This is one of the cases that the pipe was broken from one end. It was because of failure in the cap, in the end cap. And then pipes were buried in the soil, and the pressure was applied on the pipe, on the soil, and different strains were measured in different points. And our dedicated team at Center for Water Systems. Then we moved to numerical simulations. We started with finite element modeling, calibrating the numerical model, and then generating the scenarios, different scenarios for that. We exactly simulated what we had in the lab in terms of soil and pipe. And here I have another short movie showing how we did the experiments. The box of the soil box was modeled, the pipe was modeled, and the different characteristics of the pipe were assigned to the model. Then the pipe was put into the soil box. Then pipe is added to the model, and then loads and boundary conditions were applied to pipe and soil, and then the model was meshed. Yeah. Here the model is meshed, and then different parameters was assigned to pipe and soil, and the model was run. After running the model, we had stresses and strains on different points of the pipe and soil. Having this model, we were able to calibrate the numerical model with the data we got from experiments in the lab, and different parameters of the pipe and soil were calibrated. Now we have a calibrated numerical model of the soil and pipe, which is ready for the next step. I would like to give floor to Ramiz.
Thank you.
Yeah, for the next step.
Thank you very much. Good morning, everyone. My name is Ramiz. I'm a PhD candidate at the Center for Water Systems, and we're doing some digital twin and asset health monitoring. So what I can say is, you can imagine what the excitement is for a researcher after having a calibrated model. So we thought that what we could do with these calibrated models, or what is the next step that we can go on in the project. So we knew that running the finite element models, generating the models is a time-consuming, computationally expensive. So we thought that, okay, there's a case that we can generate scenarios which could happen really in water distribution systems. So we have different diameters and which thicknesses are corresponding to that diameters in the PN10 pipes. And also different buried depths for PVC pipes. Also, the let's say multiplied the values to calibrated Young's modulus of the pipe and also the soil to say that if even the aging is going to affect the pipe, we are going to capture it. And also, we have different internal pressures and external loads. So we generate all of these scenarios. And then we create all of these models, run them. It is a huge time, huge computational expense. And then we gather the data from that 4 exact cardinal points that we had in our experiments. So we have axial stress, hoop stress, von Mises stress, axial strain, and hoop strain in 4 cardinal points. And we got that data from all the scenarios. What we're doing is, okay, we have this data from all the scenarios, what we're going to do. We're thinking, okay, let's make it a bit fast. So we're looking for the surrogate model, looking for the machine learning models, or let's say regression models to use. So the first thing come to mind is looking for the white box one. Because we know some of the empirical equations that I really want to see what is the difference of the empirical model and the model we are generating from the experiments, from our finite element models. And also a black box model, which it has its own points that we have. So at last we're going to have a surrogate. About the white box, it is also obvious we have interpretability, model transparency, and also the feature importance that we can see in the equations. And also, in the black box models, we know that it is a high predictive, there are some high predictive performance, and also automated feature learning, or let's say it could catch some complex relationship between the features and the outputs. And also it is very effective with large data sets. So, the well-known one. As a white box one, we use EPR, which in Center for Water System was being utilized several times. It's a hybrid regression method of a genetic algorithm and least squared regression. So we're going to use genetic algorithm to optimize the coefficients of relationships. And also, we utilize this one, use the data, and what we did is the main regression structure that we thought could be something like a function using the features that we had the data from. And later, when you're looking at the superposition principal equation, you can see that there's a function of which the weight is the main point. The second function, which is the internal pressure, the second is the main point. And also the third function, which if none of them is happening, there is a soil weight on the pipe, which could come in. And later, this is a polynomial regression structure, which it is going to be optimized by a genetic algorithm in the EPR itself. So, we train the model. The model trained on the 3 cardinal points, this is crown, spring lines, and invert, for all the axial stress, hoop stress, for my stress, axial strain, hoop strain, and we got the equations. As you can see, for each point, each cardinal point, we have an equation which it is showing about the, if you put the inputs, the features, you will get the output of the axial stress or hoop stress in crown, spring line, and invert, and also the coefficient of attenuation of R squared is acceptable. And also in the same one, for the strains, we have the same, and we don't have time to talk more about that, But when it is transparent, we can say that the effect of each feature that we use in the model or the experiments, how it is affecting the output. And also, we have this extreme gradient boosting, sorry for the name, it is the name data. And we use this model, and we split the data for train and test. And the test shows that it's showing good, but this time there are several outputs, several inputs in the same model. It is not like DPR to have different equations for different outputs. Later, we have the surrogate model. So in this case, you will give the input features, and the input features go inside the machine learning, or let's say the surrogate model, and you will get the condition of that pipe by getting the strains output from the equations. So later on, it will come to the in situ data, which I'm going to ask Milad to come back to the scene and continue with it.
Yeah. What we have presented on up to now is what we have done in the project in the last 2 years, less than 2 years. But next step is about gathering data from live pipelines in the water distribution network and monitoring them to develop a digital twin. We are going to gather strain data, pressure data, external load through load cells, things like that, and soil moisture, any parameters which could be effectively measured in water distribution networks. And yeah, the whole system could be something like this. The parameters will be measured on the pipeline, and then the data will be transferred to a cloud, and the cloud will send the data to our machines in the university or in the company, and then we will have all of the data in our machines to monitor the pipelines real time. And fortunately, the company we are working with, Data Techniques, has a lot of experience in deploying sensors on pipelines in the UK, and now we are deploying some sensors. This month we are deploying strain gauges and other sensors, pressure gauges on pipelines in one of the utilities in the UK. And as of next month, we will be able to have those data in real time in our machines, and next steps would be developing the digital twin. And the company benefits from a high-tech solution for deploying sensors on the pipelines. And the next step is about developing the digital twin for water pipelines. Having this model, we will be able to monitor the pipes and having all of the data about the pipe, diameter, age, diameter, length, thickness, depth of the pipe, everything like that. We will have a health condition score for each pipe, and we can monitor the health condition score of the pipe day by day, and we will be able to have something like this about asset health of the pipe, and we can predictively replace the pipes before they fail. So we can shift from reactive asset maintenance to predictive asset maintenance. This is the next step for the remaining 1 year of the project, of the case project. Thank you.
Thank you very much.
Thank you.
Thank you very much, Milad and Ramiz. We have got time for 1 or 2 questions.
If there is.
How general are your results if you only worked on plastic pipes?
We started with PVC pipes, but we are at the same time doing tests on ductile iron pipes, and next step is on cast iron pipes. So we are trying to cover a wide range of pipe materials in our project.
Okay, and looks really great. Have you looked into similar work abroad, or?
There are just a few researches has been done exactly on this subject matter, but yeah, we had a literature review on this part, and also we are happy that we saw that KWR did something
Yeah,
in this
there is a
field.
model that
Yeah.
exactly the same. Thank you.
Yeah, thanks for the presentation. You went through the digital twin rather quickly, and I was just wondering, you know, we all use this term in a very loose way, and different people mean different things by digital twin. I'm just wondering, how do you define a digital twin in your case?
Take this one.
Actually, when we are looking for digital twin, yes, the definition of digital twin is a bit broad. But when we talking about the digital twin, it means that it should be a dynamic. And when we're looking for it should be representative of the same thing in the field, which we could do some non-destructive tests in our computers to look what is going to happen to that pipe or to that asset in the real time, if the situation is going to change, or let's say if, the pressure management is going to change, or any other disaster is going to happen to that. So we could just see it inside our computers to what is going to happen, and then let's say alert the utilities or the persons who are responsible for that asset itself. So this is my understanding actually from the definitions of the digital twin, if you want to add something else.
No, this is actually the definition that has been agreed by a national document that has been agreed in the UK. Now we have a document for digital twin in the UK. Yeah, exactly.
It is effectively a digital replica, which is the kind of broad definition of the data coming from the field, and then you're simulating and trying to predict.
Is it a master digital twin, a representative for the pipe, or is it a particular instance of that particular pipe in one location?
It is going to be the second one.
The second?
The latter. The latter.
Yeah.
Your tests in the lab and your simulations use a closed pipe. And so I'm interested in what happens with we know the circumferential stresses very well, but the longitudinal stresses. And if you have a closed pipe like that, the pipe wall takes up all the longitudinal stresses. But in a real system, you've got the soil holding it, but also the pipe supported at all the bends. So in my thinking is that the longitudinal stresses are not going to, the pressure is not going to be taken up. So do you have any insights onto how much of it is?
Yeah. What we're doing in the numerical model that we have at the moment is about just numerically simulate what we did in the lab. But when we come to the real pipes in the network, we have to change the boundary conditions of the numerical model. And by changing those boundary conditions, we can get to the point that what happens to the pipe in real world. When the other pipes, neighbor pipes, are connected to each other and they affect in terms of stress and strain on the pipe we are studying.
So I'll ask you next month when you get the data in the field.
In the field, we get strain from the pipes, and by applying the correct boundary conditions on the numerical model of the whole pipe in the field, and also monitoring the strains on the pipes, we can change the factors of the pipe and soil to get the correct results, to have the compatible results, and then we have a calibrated model of the pipes which is in the ground.
Hi, great presentation. I'm interested more following from the Kobus, more interested in your field application. You mentioned that asset health and then deterioration with time. So I was wondering, one of the issues that the company want to try to resolve is sensor placement. So where do you place the sensor in order to obtain a good result? I mean, what is your experience on this?
In terms of location of?
The location of the sensors, you put a lot of strain gauges, right?
That's a good question. This is just the start of a bigger project, and we are just focusing on vulnerable pipes at the moment, pipes with a lot of failures, a high failure rate at the moment. So we can deploy sensors at the pipes which have this number of high...
known defects, you put sensors on pipes, known defects,
Yeah.
Thanks. Yeah.
Do you want to add something?
No, actually, the thing is, yes, this is a very good question. And when you're looking at the asset itself, in this situation now, because deploying sensors is a something very costs very much. So we are looking for the very specific assets, putting sensors on them, And this is also, it's a pilot session. So we're looking at to see that, so we put several sensors in different positions of the pipe. So we gather the data and looking around to see that which is the best position to put if we're going to, have it for the whole water distribution network in the future.
Yeah, please. Your final question.
Just had a question on the effect of the pipeline depth. Because if the pipeline is at a relatively good depth, then the effect of the live loads may not be felt. So what stresses are you looking at? Is it just the live load or your combinations with the pressure in the system?
Combination of them. I think for the shallow buried pipes, the effect of live traffic load is more important. But for the pipes that we have in the UK, which are buried around 1 meter deep, the combination of internal pressure and external load on top of the pavement, on top of the road is important.
Okay. So at what threshold did you, from your work, do you feel that do you expect the live load not to have an impact?
Do you have an estimation, Ramiz?
I didn't got the question right.
At what depth the live load on top of the soil has no effect on the pipe?
Oh yeah, this is a quite good one actually. It's a big. There are difference when we're talking about the live loads. For example, when you're talking about the train load, we know that it is affecting more than 2 meters maybe. But about the sedan or the other ones, which we can say that it is affecting, and the distribution is coming to the 1.5 meter of the soil. But when you're looking for everything, and about the standards of the buried depth of the pipes in the utilities in the UK, they are doing some, it is around 1.5 meter, 1 meter. So we're looking for all of them.
In the lab, we were able to apply pressures inside the pipe up to 30 bar, and external load on top of the soil up to 30 tons, which is quite. And this is interesting to know that the pipes were PN10.
Yes.
Nominal pressure of the pipe was 10, but some of them were failed at pressure up to 28, 29. It's quite interesting. Italian quality.
Not the peak.
Yes.
So your asset condition curve was very nice and smooth there. Do you expect that to be the case, and or are you thinking about using something like machine learning to predict asset condition?
Yeah, actually, this is going to be the next step of the project, and we saw something in the literature, as Dragan mentioned. There are some lifetime curves for the pipes or the other assets. And we are trying to develop those curves for our assets at the moment, but this is our next step for the next year, actually. Yeah.
Thank you very much.
Okay. Thank you very much.
Thank you.
So our next speaker is Matthew. Matthew's research also has been funded by industry, and the focus is on leakage prediction.
So my name is Matthew Hayslep, and as Raziyeh just said, I work with Savić Water and to use machine learning to try and look at DMAs and leakage primarily. So some of the ways that we typically try and understand leakage that we want to look at from a data perspective. We've got minimum light flow, which you can generally see only at an entire DMA level, but the data is everywhere. There's lots of it, but it also includes legitimate demand. And then we've also got pipe failures, which are very pinpoint locations, but they're rare events. Sometimes you might have a whole year where the DMA doesn't have any, but there's still leakage there of some description. And it's also only what we can already detect, whereas we want to go beyond and see what there is that we don't know. And there's a couple of guiding principles that we looked at for our work that we did. We want to try and use explainable models because we're working with industry. We want to be able to kind of understand the models that they're using. They obviously have Ofwat that they need to report to, and we want to make sure that what we make is applicable to as much of their network as is possible. We want to make sure that what we're doing isn't just for one particular DMA, one case study, but is as widely applicable to the whole network as possible. And we want to try and not focus just on bursts and reported leakage, but possibly also unreported and background leakage as well. So, with that in mind, some of the data that we use, it is animating, excellent. So we have about 800 real-world DMAs from South West Water, about 11,000 kilometres of pipe. We look at minimum night flow records for a whole year. Now this is normally time series data, but for us, the way we started was to start simple. So we just reduce that down, basically take an average minimum night flow for a DMA for a whole year, and we'll get to that in a minute. And then, for now, we're just looking at pipe asset data. So we've got length, age, diameter, material, and total number of properties that are connected to that pipe as well. And what we want to try and do, like I said, is just starting simple, try and predict some average historic minimum night flow, right? If we can use the asset data to sort of say, this is roughly how much minimum night flow we're expecting, then we can kind of explain some of the differences. Why does this DMA have more minimum night flow than this DMA, right? And then we can try and drill down further into leakage. So what we started with was making a whole bunch of features because we start with the pipe data, but the thing that we're trying to predict is at this DMA level. So we look at things like total pipe length, average age, minimum diameter. We made something like 200 human features to try and do some machine learning on. And so the first attempt that we get looks something like this. We trained a very simple linear model, so it's nice and explainable. And down at the bottom we've got our observed average minimum night flow, and up the top we've got the prediction that we make. And you can see it's doing a reasonably decent job. Because it's a linear model, we can say that we're able to explain 65% of the variation in average historic minimum night flow between all of the different DMAs. But it's quite a lot of features that we're using, and there's a little bit of complexity there. So as a follow-up to this, we did a piece of work with genetic programming, where we wanted to try and find some kind of minimal set of features that we could use to do the same experiment, basically. And we got very similar results. With only these 5 features. And we won a Best Paper Award at Gecko a couple of months ago for that work. And this brings me on to the explainability. We wanted to try and exploit this because we know exactly how we go from our pipe data to our features, and we know exactly how we go from our features to our prediction because we're using a linear model. And can we exploit that to improve the capabilities of what we're doing? So we kind of combine this to sort of say we know how responsible each pipe is for each feature, and we know how important each feature is for the prediction. And we combine that into what we call the leakage contribution score, which is a number for each pipe which tells us how much it's contributing to the leakage in a DMA. And the convenient property of this is that if you sum up the leakage contribution score of every pipe in the DMA, it's roughly equal to the original prediction. But how do we test this? Right, we've got a little bit of a problem, so we go back to pipe failures. Right, we look at repairs and replacements because they have pinpoint locations, so we can attach them to pipes. And we do a classification problem now. It's a different machine learning task. So was a pipe repaired or replaced in the same year that we're looking at the minimum night flow? And then we can use this leakage contribution score as a comparison to other models that we've made. So the blue line here is the leakage contribution score that I just showed you. So it's a number that's trained based on minimum night flow, but it has a predictive power for predicting pipe failure, which kind of suggests that it's actually sort of looking at something that is meaningful, basically. But unsurprisingly, it's not as good as machine learning models directly trained to do the problem, which makes sense. So can we do better? So we wrote a paper about this, and then immediately I went back to this kind of mental model that I had, and I thought, what if we just scribble all of this out? And what if we can just go and skip all of that part and go straight from pipes to leakage contribution score, basically. So we kind of formalised that and said, okay, what if we say the minimum night flow is exactly equal to this leakage contribution score that we want to find for each pipe, and then we sort of say, okay, well, we'll keep it simple for now. Leakage contribution score is equal to the linear regression equation. Nice and easy. Now, it's a lot more complicated finding those coefficients than it might seem at first glance. If you want details, poster number 6. But it worked. The minimum night flow predictions are not quite as good as the previous model. As you can see, we've lost about 0.2 in our R-squared, which is quite a lot. But I think that that's mainly because we're losing some information. Instead of looking at the whole DMA, the model's now looking at each pipe in isolation. So you're losing out on relationships there that we want to try and capture later on. However, the black line here is our ability to now predict pipe failure, right? So we're now as good as models directly trained to do that problem. So not only that, we're actually, strictly speaking, predicting how much minimum night flow each individual pipe is responsible for in a DMA. So we've managed to kind of increase the resolution almost in a particular way. And really this is our only way of validating whether or not we're actually doing that, because it's difficult to measure. So I feel like I've gone quite quickly because this is my summary, is that we've been able to essentially go from just minimum night flow to create a model that can predict both minimum night flow and pipe failures, essentially. And that's obviously, like I said, important for areas of the network and DMAs where you don't have many pipe failures, but you still have leakage and you still want to know what's going on. So I expect many questions.
Yes, please.
Have you got any information about, as some, has people opened up pipes and tested them for background leaks? Do we have any idea, is it most pipes have a little bit, or is it just some pipes? Do you have any sense of what that looks like from?
Yeah, my understanding is that most pipes have a little bit, but it might be, tiny little drips. I can't think of the right word, but it's just leaks and seeps, basically, from stop taps or junctions and seams and things like that. And then maybe that correlates with age and pressure and a lot of other things that we're not looking at the moment. So I would have thought that most of the pipes should have a positive number of some description. It should all contribute some amount, even if it's very small. And this kind of seems to work with one of the most important features in basically all the work is the length of the pipe. Right? If you've got more pipe, you get more leakage. It's pretty obvious almost, essentially. But that kind of backs up that thinking that you essentially have a per meter amount of background leakage that you should expect.
If I could just add something to that comment. One of the clues we have for background leakage is when they do fix all the pipes and they do pressure and leakage test on background leaks only, they get a leakage exponent of about 1.5.
Yeah.
And that would correspond to all the leaks being closed without pressure and only opening up when there is pressure. If that's the case, they're all sort of weeping, very tight openings or seals. That would explain that. So that sort of aligns with what you're saying. That it's very widely distributed
and on the back of that as well, because we're looking at minimum night flow, that will be when the pressure is highest because there's the least usage, right? So that might be exacerbating that in the data that we've got.
Great.
Thanks for a nice presentation. In the minimum night flow method, leakage is defined pretty much as the difference of inflow, which is being measured, and the consumption during the night. Measuring the inflow is relatively straightforward and reliable.
Yeah.
Consumption is the part you need to get right.
Yeah.
I haven't seen in your list of features anything to do really with the night consumption.
Yeah. So the only thing that we've got is the number of property connections, essentially. So one of the things that we can do with this, because we've got a linear model, is we can sort of say, factor out the number of property connections. We can make the prediction, train the model, hopefully the model will pick up some relationship between the number of connections there is and the difference in minimum light flow, because you'd expect there to be maybe like an average amount of usage in the minimum light flow periods for each connection.
But one of the thorny issues is non-household consumption.
Yes.
It's always been a thorny issue.
Yeah.
So how's that dealt with?
So at the moment it's not. In the future, I've got some data on not just number of connections, but what kind of connections there are as well. So whether or not it might be hospitals or commercials that have got a 24-hour kind of pattern. And so if I can put that in the model, hopefully you can pick out those particular things. But yeah, there's substantial issues for minimum light flow in general.
Yes. Southwest Water has a number of smart demand meters, with quite detailed data about the consumption they monitor, as far as I know.
Yes.
I don't know if this is present in this area or not, but there are areas where they have this.
Yeah, usually, so the minimum light flow basically comes directly from what they report, what they use to report to Ofwat. So if they have got large consumers that they use and those are metered, they are generally taking out the minimum light flow.
This is a general point. Do you think that Southwest Water's accuracy in the reporting of their leakage is robust?
No comment.
You just answered my question.
Thank you.
Yes.
I think I understand why you decided that explainability can be only done through a linear model in this case. But computer scientists are very good at coming with explainable methodologies. Have you tried a non-linear model and then use some of those methodologies to explain?
So some of the classification and regression things that we did very early on were with neural networks and random forests and support vector machines and all these kind of things. And we basically found that the difference in performance was negligible, essentially. So why would you not use an explainable model in that case? And for this work in particular, I think that we want to move a little bit beyond linear regression, but I still want to keep it explainable. So I think something like EPR, where we can figure out an equation, I think that's really helpful. Because you can take the equation out of the machine learning context and just give it to engineers. And they don't have to use it with data, they can just sort of say, okay, well, this makes sense with what I experience.
Thank you.
Okay, thank you very much. So, our next speaker is Shuming, and she is looking at background leakage.
Hi everyone, my name is Shuming. I'm a PhD candidate in CWS as well. My supervisor is Professor Raziyeh and Professor Edward. So my work is mostly focused on gradual leakage detection for water distribution system based on statistical method and neural networks. So at a very early stage, we published a literature review last year to identify the knowledge gaps and what's the disadvantages and advantages of those model-based, data-driven leakage detection methods and burst detection methods in the literature. And we identified three of the limitations in the literatures we identified are shown on the PowerPoint. The first thing is that the majority of the published papers, especially for data-driven method, they are assumed that the anomaly they detected are burst events, which means that the anomaly happened in a very short time period and they reaches to its maximum value. But however, in some cases, and also they rarely mentioned online settings, they didn't address the problem caused by environmental issues. What we want to mention is that in reality, some cases the leakage happened in a very long period. For example, the left-hand side two figures shows the exact same amount of leakage events, but the second leakage happened gradually growing for months, which results that it doesn't have any distinguished abnormal behavior that basically disobey the assumption most data-driven methods made that the anomaly they detected have distinguished abnormal behavior than the normal, but the gradual leakage they didn't. So how to detect, and also not to mention that there are some global trends in the data itself. For example, from the water demand increased from summer to winter, decreased from summer to winter. I sincerely apologize for that. And this can also ambiguous the existence of a gradual leakage event. So our first work we published early this year in Journal of Hydroinformatics is based on a statistical method and a purely online framework to detect these gradual leakage events. And the online leakage detection system based on EWA is based on a statistical method called EWMA Enhanced Two-Key Method, and involved robust statistics, which is robust to the data noises and uncertainties in the data, and also it could adapt to the time-varying characteristic of the flow monitoring data, such as the demand increasing from spring to summer, as we mentioned before. And this method has three subsystems: the pre-processing, online detection, and also a feedback control to control which part of the data is what we should use to update model and which part of the data we should be abandoned. So this is the results, and we applied our method to a synthetic case study, which is a L-Town network published in 2020 in CCWI. So it should be noted that even though this is a synthetic data set, this network is created based on a real time in Cyprus. So every node, it has a year of demand pattern with lots of uncertainties and noises. We use this network to generate a year of flow monitoring data, and like the left-hand side figure, with 4 gradual leakage events assumed to quadratically increasing over like between half months or to 1 month, and 2 burst events in the data set. The results, this is one of the comparison. For the details, I didn't mention here because of the time limitation. The results shows that the proposed method has highlighted the existence of gradual events and burst events, and also the time-varying structural setting strategy has adapted to the uncertainties in the data and greatly emulates the opportunity of false alarming. However, due to the limitation of the statistical method we proposed before, it has some accuracy limitation. It's not as accurate as the data mining models, very state-of-art method like machine learning neural networks. So we propose a new method that based on machine learning to learning the data pattern automatically instead of using the mean or deviation or quanta or anything else that the statistical method used. And in order to highlight the existence of gradual leakage events, we first extend the prediction window. Instead of using the traditional 1-point forecast, because it doesn't have any historical memory, you only want to highlight the existence of the abnormal value at the current, but it doesn't have a time window memory. So we extend this, and we create a map. We use neural network to create a mapping function between the input and output. For every time step, we generate a pair of observation and prediction, and then we tried lots of distance calculation like Manhattan distance, Euclidean distance, and then we find that cosine distance is the most robust one to highlight the existence of leakage while minimizing the pattern of false alarm. And then after the residual generation, we get the residual vector like the top figure on the left-hand side. It could be seen that there are some sudden spikes in the error residual. This is because some unexpected noises and unexpected user behavior in the data, and the prediction model is not perfect all the time. So at this stage, we need EWMA to smooth the data set while maintaining some information in the historical as well. And at the last stage, the threshold setting will be static because the abnormal events has already been highlighted. In this time, we, instead of using 4 or 5 gradual leakage events, we create a 6 leakage level. Each level have 100 gradual leakage events. Like it increased, started from 0.2% daily increase leakage flow to the daily consumer demand, to the 1% of the daily consumer average demand. If we can see that at leakage level 1, the gradual leakage events cannot even be seen from human eyes. Only when it reaches to leak 6, it can be seen after it fixed. If we cover this, it's hard to distinguish there is anything happened. So it is crucial to detect it before it reaches to its maximum level and create some consumer complaint. The left-hand side figure shows that the comparison between the traditional one-step forecasting and the multi-step forecasting approach we proposed. It can be seen that the traditional one-step forecasting model will consider the gradual leakage events as a normal scenario, and it will gradually adapt to it. It doesn't show any abnormal behavior in the residue generated. And unless at very large leak level, at the end when leak stopped, it has a sudden decrease or sudden increase in the flow, it will get some error, but at that time the leakage has already been repaired. When you alarm, and alarming there is useless. So after we did smoothing, we did threshold calculating, we can generate the final ROC curve. It should be noted that we couldn't reach this to the top like 99% or 95%. Is because at very early stage of the leakage, it only have like 0.01 or 0.02% of the daily average flow. It is impossible to raise an alarm there because the leakage is not even larger than the data noise itself. So, and with different leakage level, we have tried our best to detect all the abnormal points as we can. And the red star shows where is the 3 sigma threshold setting at. It can be seen that with 3 sigma rule, already lots of false alarms has been reduced, and we reached our best to the TPR. And then we apply our method to a real case study, the data we collected from Severn Trent water. And there is a gradual leakage event happened in November 2021. And we compare, because this time the gradual leakage event is pretty huge. So even for one-step prediction model, it has some error at the end. But still it shows that our model performed better than the traditional one. And this paper published early this year in Journal of Water Resource Planning and Management as well. Thank you.
Thank you very much, Shi. Any questions for Shi? Yes, please.
I've got many questions.
That's fantastic. That's the idea behind the session. Yeah, please.
What I'd like to know is, I mean, one of the interesting things for me is how leaks develop over time. You know, what is the process? Are you able to characterize different patterns of how leaks, you know, gradually increase their flow rate and what that pattern looks like?
Yeah,
your analysis.
Yeah, in the first study, we used the same assumption as the one they used in the CWI is quadratically increased, like it's ax squared plus bx, something like that. And we discovered that it's harder to quantify it. So, and then at second stage, we just use simplified one, like linear increase. But when the leakage increase rate is very small, it shows no big difference with the first one. Yeah, that's how we assume it. But in real life, it doesn't happen like that, for sure.
Do you mind showing the last slide, please? That end of the pressure signal, okay?
Yeah.
That looks to me potentially as a sense of drift, not necessarily leakage.
We look at
Do you have any independent evidence that this was a leakage?
we look at the customer report, and they said that there is a leakage.
You mean
Because that's a
work
typical-
orders,
That's typical
company.
sensor drift. That's the way how the failure of the sensor manifests itself.
Sorry?
The last part of the blue line over the end in December, November, end of November, pressure going down. This part.
The drop.
This part. That's how sensor drift typically manifests itself. It's a failure of a sensor, not a genuine event, not necessarily a leak.
Oh yeah.
But you have other evidence that it was a leak then?
Yeah, it is possible that the gradual trend happened in the data, not always caused by the leakage. So in our next step, we plan to propose another method that incorporate the information from multiple sensors so that we can decide if there is a real leakage event happened or maybe just
coupled with the works management database where they record the actual leaks.
These are based on the, so basically 7trend has provided time series data for the work orders. So these are definitely, but in other cases that we are not aware, as she suggested, looking at multiple sensors to avoid false alarms. Thank you. Yeah.
Yes, two questions.
Yeah.
First one, have you compared this one with other papers published using that network, because that network has been used for several papers in Journal of Water Resources Planning for this topic?
Yeah.
The first one.
Yeah, that.
Second one, you tried several methods, especially for the distance, and you said the cosine distance gives you the best result.
Yeah.
Have you thought about why the cosine distance gives you the best result? Why, Manhattan distance cannot give you the best result when you compare the different features?
The cosine distance, it focused more on the similarity and the deviation. I haven't think about that thoroughly, but it's just a distinction that it detects the similarity between the two vectors, and it doesn't consider much about those big deviations of single points like Manhattan or Euclidean. Like you will easily calculate that into the final residual vector. And back to the first question, I got that question from multiple reviewers several times, and so yeah, I studied all those gradual DIM papers as well. First of all, I didn't use as many information as they have. I only used flow data, and I didn't use pressure sensors or smart meter sensors or anything else. This is only based on flow sensor. And also, the original battle DIM, they create data set with simultaneous leakage, but we don't have. So in here, every leakage one leakage happened at a time. In their case, simultaneous leakage happened all the time. Like maybe there are 2 or 3 leakage events happened at the same time, and I have to confess I'm unable to do that right now. Because first of all, we didn't use that much information. Second of all, yeah, that's all. I didn't use that. And also, I look at some papers, and actually, what surprises me that this is online leakage detection. So all the data happened after. I didn't know. The algorithm runs forward like this, and some of the methods. They are actually using the information after. They are like getting the group of data and get rid of the trend, get rid of the seasonality. But I didn't do that as well. So yeah.
And just to add to that, we presented some initial results to different water companies, and the first thing they were saying that we don't have that much information about our system. So basically
thanks for being here. I am Varshith, first year PhD student, and Professor Raziyeh is my first supervisor, and Professor Peter is my second supervisor. First of all, I need to give a heads up. I am not using any artificial intelligence here, just a human intelligence and my laptop to get my work done. Here is the topic which I'm going to discuss, that is optimal placement of pressure sensors in water distribution for leak localization. If we look into the existing problem, one of the major problems faced by the utilities, especially in the developing countries, is the leak management. And if we look into the numbers, I had an opportunity to work with real case studies when I was working with Hitachi in the past. The actual leakages, even in a relatively new networks, in certain DMAs, it went up to 45% of the bulk supply, which has been a major concern for the utilities, but then they don't really disclose it. When we went to estimate the leakage levels in the system, the site engineers, we said that, okay, you have a leakage of 45%. The site engineer said like, okay, please reduce the number to 25, and you say it to the chief engineer because he would be mad with us. Likewise, there are many issues with leakage. What can we do is, one of the most efficient methods is to pinpoint and repair existing leaks, but the major challenge here would be to search the entire area to pinpoint leaks and then repair the leaks, which makes it very infeasible for the utilities, both in terms of money spent as well as the time required, having how large the DMAs could be and how expensive the technical labor is to do that particular leak localization there. What can be done is, to improve this approach, we can provide ICT solutions to localize leaks and reduce the search area, maybe utilizing the sensors, thereby reduce the time and effort to localize leaks and pinpoint, and then thereby help in the leak management process. And a few of the popular methods which we know is hydraulic model-based methods and data-driven methods, etc. Here I am focusing on hydraulic model-based methods, and how beneficial this solution could be is how effectively we could localize the leaks. The methodology is able to localize the leaks, and there are certain challenges in that as well. Any important step in leak localization would be, or the crucial part would be, efficient leak localization is only possible if the leak event is captured by one of the sensors. If it goes undetected, we never know whether a leak event has occurred. To ensure that we generally place the sensors at the most sensitive nodes to capture most of the events. For that, to identify those sensitive nodes, we perform extensive hydraulic simulations there. But the challenge is, will these sensitive nodes have the same sensitivity forever? As we know, since we are using pressure sensors here, both demand and leakage have same impact on pressure, similar impacts on pressure. And during the recent times, in the pre-pandemic and the post-pandemic, we have seen a shift in the consumption patterns. That is, there is a shift in the consumption patterns because of the work from home paradigm or stay-at-home activities. So those sensors that were designed using sensitivity analysis of similar approaches, maybe in the pre-pandemic time, might not perform as desired when we use the same now or during the pandemic times. What can be done to ensure the robustness of the proposed sensor configuration under different possible scenarios? So we came up with the sampling design methodology for optimal sensor locations, and the key features for robust sensor configuration, which we think are the first and foremost, the most famous approach is finding nodes with high sensitivities for sensor placement. Second is placing sensors at nodes with higher topological importance, using how the network is spread and just the network connectivity. And third one is maximizing the spatial coverage of the sensors in the water distribution. When we went to the utilities, they say, okay, we can only afford 3 sensors. Usually they go with the bargaining thing. If you say we need 5 sensors, they would be like, we can't really afford 5, so can we get you to 3? When we say 3, okay, fine. Then we'll say, okay, spread it across. Then if we are insistent saying like, if we place the sensors in a certain area, we can get most of the information. They would be like, no, we want to use it for other purposes also. So please maximize the spatial coverage. For that reason, we introduced this explicitly here. For finding the sensitive nodes, we did a thorough sensitivity analysis, simulating leaks of size ranging between 0.5% to 8%, though 8% seems to be a burst, but then we did so. And identifying those nodes with higher sensitivity, which are impacted with maximum pressure deviation when those events has occurred. We identified such nodes. To find the nodes for the other two objectives, we used graph theory based approaches, where for the second objective we used a bitwidth centrality of all the nodes is calculated for an edge weighted graph. For consistency, the edge weights used for the graph are the pipe lengths, and basically the nodes with higher connectivity, the other nodes are identified. And for maximizing the spatial coverage, we used a Steiner tree based approach, where a Steiner tree is constructed or else identified for that connects the potential sensor nodes. If we see to construct any stainer tree, we need a terminal nodes, and stainer tree is a tree, as you can see here, that connects the red dots with a minimum possible length or else minimum possible edge weight here. And those other nodes C and D, which are not terminal nodes of the sensor nodes here, which are essential to construct a stainer tree, are called stainer nodes. And we implemented this in a case study, L-Town. The reason why we chose that is that it is a benchmark one, and second is the network itself has 33 sensors. So to compare or to benchmark our sensor configuration, we would have certain thing to compare with to evaluate our sensor placement methodology. Here are the sampling design results. These are the sensitivity analysis results. And when I started using graph theory and those things, I learned certain things which I didn't know earlier. One thing is called assortativity, is how well the nodes with similar features are connected with nodes having similar features. Usually water distribution networks are assortative. That means if we see nodes with similar elevations are connected, fall into the same place. Likewise, one good thing that happened was, even for the sensitivity, the same thing repeated. When I assigned the sensitivity values as node weights and then calculated the assortativity, the value was around 0.98, where the maximum value is 1. So we can clearly confirm it is a well assortative system. And here are the results for the 33 sensors. To be on the same ground, they have 33 sensors and I propose 33 sensors. But my methodology actually avoids placing the sensors at the boundaries, since I'm more focused on the topological importance, unless they have higher sensitivities. If you see, the sensors in the top portion fall into the boundaries just because they have higher sensitivities. And to evaluate both the sensor configurations, we use some leak scenarios for evaluation. What I did was, I simulated leaks of size 2% of the bulk supply, and for that I selected 5 nodes at random. These are not simultaneous leaks but individual leaks, and one spatially distributed leak, which in this case these are simultaneous leaks, where the total leak size is 2% of the bulk supply, and results are compared for successful leak localization and predicted leakage amount. Just to compare, I wanted to see how far these leak locations are from the existing and the proposed sensor configuration. Out of the 5 individual leaks, 4 are closer to the existing sensor, one of the sensors in the existing configuration rather than the proposed ones. So it gives a better advantage to the existing sensors. For leak localization, what we used was leak localization and area leakage estimation, using an in-house leak localization to develop using generic algorithm and pressure and flow data. And here are the results. This is the individual leak, and this is what the algorithm localized to. Likewise, all the 6 events have been successfully localized, but the size of leak localization has changed with the location of the leak because of the sensitivity values. And at this stage I was really stuck, because both the sensor configurations actually gave good results in leak localization, but I couldn't really see which one was beneficial. So I had to add few lines of code and then see what is the estimated amount of leakage. That is where I saw a major difference. Though all the leak events were successfully localized in both the scenarios, the proposed methodology when we use the proposed methodology, proposed sensor locations, the methodology was able to estimate the leakage amount closer to the actual leak in 5 out of 6 scenarios. In this case, when we use the existing ones, it predicted the leakage amount lesser than what it actually is. These are not for single iteration. For each scenario, we ran the leak localization algorithm thrice, and the mean values of leak estimation error were estimated for better comparison. So from this, we could conclude the proposed methodology has got proposed sensor locations performed better than the existing ones. In the later stages, we would want to reduce the number of sensors, as Professor Raziyeh mentioned. Having 33 sensors for that size network is a big deal. And if you go to India, they would say 2 sensors, not more than that. So in the later stages, I would try and reduce the number of sensors without actually compromising on the leak localization potential with that. This concludes my presentation. Thank you.
Any questions for Varshith? Yes,
Well, I try to have two questions together.
please.
Thank you. First one is, normally this question will be raised by a reviewer when you submit a paper. So using the pressure sensor, how to tell it is real leakage or big customer demand? Can you tell this one if you have signal using the sensor from the pressure? That's the first one. Second one is, what is the minimum leakage, or what's the minimum flow you can detect using different sensors? Or do you have a relationship between the minimum flow you can detect with the number of sensors?
To answer the first question, actually, both have similar effects and we can't really delineate. But then, to see whether it is a leak or it is a higher demand, what we actually plan to propose a sequential approach based on estimating the real losses from the water audit studies. We have the flow data, we have the consumption data, thereby we can estimate what is the leakage that is occurring in the system, and you limit that for calibrating the demands, thereby we could delineate leaks and demands to a certain extent, but not accurately. But just using the pressure data alone, it will be hard, according to me, it would be hard to delineate between abnormal demand and leakage. And I forgot the second question.
All right, second question, okay. You said 2 sensors or 3 sensors. I think the number of sensors you resolve will be connecting with the minimum flow you can find as a leakage. So do you have any relationship between the minimum flow you can detect with the number of sensors you place on?
It has many dependencies. In this case, since the major focus is only comparing the different sensor configurations but not on the leak localization case, I did not consider any demand uncertainties. The major assumption in this particular case is that all the demands are the true demands and only leakage has occurred. Thereby, I could actually localize leak up to 1% of the bulk supply using 33 sensors. But the relation between the number of sensors and the minimum leak it could detect, I really have to establish the results in the later stages of the work.
So you're talking, first of all, I'd like to commend you on the approach, because not many researchers have done sensor location design and this localization as one kind of problem, because they are related, and they would do first sensor, put sensors, or optimize the sensors, and then look for localization. So that's really good. And also, if you can go back to the slide when you have 3 objective functions or 3 measures that you're looking into.
Yes.
So if I look into the second, and I try to understand, and my simple understanding is that the 2 measures there are related to the distance. Have you considered looking into resistance as well? Because that's what between us could have, and it may give you a better relationship between points.
I'm sorry, Professor.
Flow resistance.
Oh, flow resistance.
Because pressure is related to the resistance in the pipe.
I didn't really consider that, Professor. The reason why I did not use that, you mean the energy losses?
Yeah.
In the literature, I have seen 1 or 2 activities using that, but considering there are challenges because since in case we don't have a well-calibrated model, the spatial and temporal variations in demand can, and the time when we are the timestamp when we use the model to get the sensor locations, every time we run it might give different results. To get some consistency in terms of spatial coverage, I went with one standard, which is length there instead of the head loss.
So you think that the length is better measured than the
hydraulic loss?
Hydraulic loss.
For consistent results,
okay.
I use that.
Okay, thank you.
Any other questions? If not, thank you very much. So may I ask all our panelists if you could please come to the front. Sorry.
There you are. Lots of questions. I was supposed to choose. A lot of questions, so you have to answer.
Yeah, thank you very much for agreeing to. If you like, you can bring the chairs forward. This thing is.
It's good as the bottom is not.
Thank you very much for agreeing to do this panel discussion for this session.
The screen, please.
Sorry.
Yeah.
Shall I close it?
No, we did a full presentation.
When I'm doing, it's going to another slide. I don't know what is happening. Okay,
Yeah,
perfect. Yeah. Okay, great. So, yeah, I'll open the floor, please. If you have any questions.
Well, can I just say before you start, I was so impressed with the work being done. Well done, everybody. So much good work going on in the center in this area.
Thank you. I think it might be better if we start with each panelist, your views on asset management, future of asset management, how AI or other new technologies may influence how asset management is going to be done in the next 5-10 years. Shall we start with that question while participants think about their questions? Yeah?
Kobus asked the most questions, so he should be the first.
Okay. Kobus, are you happy to start?
Yes, I have no idea.
We'll call this session Drop Your Friend In.
I mean, what I tend to work on the detailed understanding of leakage behavior and asset deterioration, and I think it's going to have to be a combination of understanding the deterioration processes and using big data and AI to combine it. And the better we can understand how pipes deteriorate and we can identify that, the better we'll be able to use asset management. So it's going to have to be both. And I think one of the biggest obstacles we have is good data. I was really surprised. One of my PhD students is doing a stochastic model for leakage in a DMA, and we did a similar study earlier, but we didn't differentiate between different leak types. So I said to her, go and look for literature about the types of leaks that you find in different pipe materials, distribution of longitudinal, circumferential, round hole cracks, and what are the dimensions of these things. And we found two sources that gives a distribution for different materials, but absolutely nothing about the dimension, lengths, widths of cracks and holes, which for me it seems really important to know if we want to understand how did they get to this and how long were they there. So we've started some work and we've got a paper under review at the moment. Anybody's reviewing it, please.
Be gentle.
Yeah, be gentle. I think for me, we need to do two things. On one hand, look at the AI and the big data and all of these techniques, but on the other hand, really understand the processes and gather fundamental data as much as we can and make that much more of a process of documenting that stuff.
Absolutely. We did a review of UK water industry research has got a database and all the water companies contributed. So we did a review, actually KWL was involved as well. So we were looking internationally to see how to improve kind of standardize the data collection process and have a good data. It's very interesting that when we were looking at data they had from what we get usually from companies for different purposes, it was very different. So it seemed to me it was more like tick boxing exercise. They were asked, give us this, and they gave, but they had some other data as well in another department. So yeah, the conclusion of that review was more needs to be done. Yeah, just learning from best practice internationally as well. I think in UK it's from one company to other company there are a lot of differences as well. For example, currently when we talk with one, they say we've got only flow meters or we've got only few pressure meters. When you go to another company, it changes company. Thank you. Anyone? Yes, please.
Maybe if I can follow up on that. I like the presentations today. I like that this is still a very much research active area, even though research on this started a long time ago. And I fully support what Kobus was saying in terms of that we should be looking across, approaching this from different angles and by using different methods. AI, data science on one side, experimental work on the other side, statistical methods, everything else. But I kind of feel that, after reading all these papers, after a number of years and so on, that we are kind of, massaging just new methods into similar data sets and that we are struggling. And I think that the obstacle is really the data at the moment. And we should probably do something about it as a community. We are not the ones who are collecting the data, but maybe we could at least raise awareness somehow.
I think data consistency bedevils everything.
Yes.
And if you think of just taking UK water companies, they're just project management organisations. They don't actually do anything. They third party everything. So the consistency of their data collecting contractors, whatever that data is, they're never going to have 100. They're never going to provide consistency because they don't manage those data collection contractors uniformly across their business, and that's the bedeviling issue, I think.
And there's no quality assurance, I'm sure. You just
Yeah, absolutely.
And there is this move toward data as a service that you may have heard of. So where instead of a company collecting the data and doing the quality assurance and so on, they basically subcontract. Yeah. And maybe there is some light there, if that subcontracting done in the right way, and maybe there will be more consistency in the future. But I think we as a community could, as a minimum, I don't know, raise awareness, maybe write an open letter or submit a discussion article in one of the journals, basically, doing a brief review and saying, yes, all these methods have been developed, they have been successful up to a point, but we are now reaching the point where without additional data, we won't be.
Even Cambridge prisons water.
So,
that could be a discussion.
Something like that. And the other thing I was going to mention is the need for good benchmarks. I've seen few people use the latest benchmark from the competition. I was part of the team that created that benchmark. That benchmark is more artificial in nature than you think, than it appears. Because again, we couldn't get all the data we wanted. The people from Cyprus didn't have access to limited data. So we had to compromise, and we at least tried to, what we created artificially, we tried to mimic reality as much as we could. But there is definitely a need for a good set of benchmarks where we could start comparing these methods more thoroughly. Because I see a lot of new methods coming up into journals. Sometimes they are compared with another method from the literature, sometimes they are not. Even when there is a comparison, it's not consistent. Different people use different metrics, different examples, and so on. It's very hard to say then what works better and so on.
Yeah. But as we were discussing at the online meeting regarding benchmarking, requires good set of assessment criteria, because same benchmark can be modified and used in different ways. So it requires some effort, to make sure it's done properly.
Even more than that. But my concern is that that particular group, which is the student of Aviosfield, created this kind of initiative and so on, but they're really it seems they're pushing toward pump scheduling and that sort of benchmarks. We really need some benchmarks in the leakage community as well.
hopefully with open data, other things, some water companies are willing to share maybe more data. Also in UK, Afvat recently announced they are, for innovation fund, they are allocating 100 million more, and it will focus on efficiency and data. So hopefully that will encourage water companies to do
Hopefully
more.
things will improve, but
Yeah.
we all know pretty much more or less what kind of data companies already have, and we need to encourage them to go out and collect more data, different data, and provide contextual information as well, because quite often you get a lot of data without much context, and you really struggle to understand it.
I agree, and I think we need to think more about the, sort of the end-to-end project as well. So thinking, what is the data being collected for? When, we have the machine learning algorithms in the middle, or other sorts of statistical machine learning algorithms in the middle, and then there's the sort of decision support and the human AI kind of interaction at the end. So what actual decisions are we going to make on the basis of the data and the models that are created? And I think we need to think about that process from a sort of an end-to-end kind of idea, so that we can gather the right data in the first place, that gives us the right outcomes at the end.
Yeah.
Yeah, so sorry, I'm a little bit nervous, so first time sort of contributing to the discussion, but I'm representing one of the utility companies, so just to defend a little bit, so on the data collection subject, we do have a lot of sensors, a lot of systems, new protocols are being available, so our challenge, and we've got obviously our own overarching SCADA systems, where all the sort of old school data end up. But now with the new sensors, those are actually not being collected to the same system. So I think what would be good, and the challenge we've got would be to have one like an integration platform where all this data can be fed to, going from our old school sensors, from PLC systems, from SCADA systems, and also from the new types of sensors, so IoT, other protocols that are being made available right now, just to have this one platform where all this data can end up, and we can sort of compare them in an easy way. And those platforms are available. There are platforms available right now, but the other challenge is that there's no so much incentive right now for us to invest in this system. So that's why there are certain projects like control rooms of future, where there is one overarching interface where all this data can be fed and displayed for the control purposes, for the operators and controller in one system, on one monitor. But there's no, or there has not been so far, much of an incentive from industry regulators to invest in that way. I think we're doing some work already in that area, but it's just very new and very fresh at the moment.
Yeah.
Share them with us.
I can just add to that. I mean, yes, you are right. Not just your water utility, others are collecting more data, additional data. Some acoustic sensors are being installed, and so on. But still, the past has shown that just by small increase of sensors, you can do a lot of good. The project I did with United Utilities pretty much 15 years ago, we started with a 1 flow meter per DMA just at the entry point, and pressure monitor at the critical point. And even that was good enough in many cases to raise an alarm. We couldn't pinpoint the location of a burst, but we could at least raise an alarm. But then we persuaded you and Yorkshire Water at the time to install, I don't know, half a dozen of sensors in a DMA, or in some cases a dozen of sensors. So get to the density of like, I don't know, 200-300 properties per sensor, rather than 1,000 properties per sensor. And then we could even start looking into not pinpointing, but again looking at more precisely at the location. So I appreciate that you need to build a business case in the utility, and that this needs to be pretty much, someone needs to pay for it, let me put it that way. But this has been going on for a long number of years now, and I'm just surprised that that's still being discussed, that there is still no kind of business case and justification for doing this thing.
Yeah, that's a good point, and also in the old school ways of doing things, all the sensors and all the data are actually going through our control systems, and so through, like in traditional way, it has to be wired into a PLC, then makes its ways through network systems to our SCADA systems, and then you can extract, or that SCADA will have a historian element or some trending elements, and this is how you extract the data. I think that we've already changed our approach, and it's sort of in a concept at the moment, but not all the data has to go through our control system, because that is quite expensive. So if the sensor is not actually used, or that value, that measurement is not used for control in any way, is just to provide an insight to what's going on with that asset, it can actually bypass the control system and just go straight to the data lake or somewhere to a data repository.
And then going through a control system can have other side effects. I know that in the case of one of the companies, it took up 2 hours for the data to go through the SCADA system with the systems they had at the time, including some, probably human-related, approvals of this or that. And they managed to reduce this to half an hour, but that's still a lot, if you want a timely detection. Still, it can interfere with that as well.
And there are also obviously capacity restrictions as well. Those systems can't accept unlimited number of data. There are some limitations, whether this being just number of data points or as you said, the time it takes for that information to propagate through the system and actually be available to view.
So I am from the business school and my background is not engineering, so apologies if this is the question I'm going to ask. Yeah, it's very simplistic. But I've heard during the discussion a couple of times being mentioned that it is difficult to know whether it is abnormal consumption or it is a leakage, right? And I'm just trying to draw some parallels with, let's say, the electricity, again an utility, and the use of smart meters, right? It has come to a stage where, people having solar powers are able to sell that to the grid itself. This thing about detection, is it really so difficult if you have a smart water meter and, you know how much flow is coming? So that was...
That's where the issue is, you have widespread smart electricity meters, but not so widespread smart water meters. I think in the UK as a whole, still good proportion of properties is not even metered, let alone smart metered.
But that would be a solution.
Yeah, that would be a solution. Yeah. Then you would monitor the consumption and have a lot better information about consumption, not just residential, the other as well.
But Thames is moving big way into smart metering. They're going to have in 2-3 years, they're going to have 90-95% coverage. Household, yeah.
But I can tell you in the Netherlands, there are no smart meters at all for water. For electricity, pretty much every house has one.
What is the average leakage there?
The leakage is small, 5-6%, with extremes being 9% maybe. But that's to do with a different type of asset management. They replace their pipes more frequently. There is more funding for that, which immediately cuts the leakage down. And people say that the type of soil, which is the sandy type of soil, kind of naturally clogs the pipes and reduces leakage. Yeah. That's a theory to be proven.
They believe it. The UK water professionals, they don't believe the Dutch. They've sent 2 missions to the Netherlands in the last 20 years. They got the data, they were doing their computations together with the Dutch, and they still can't believe how low leakage is.
The pipes are definitely more frequently replaced.
Yeah, by the 1970s they replaced half of their systems already. They're slowing down in terms of asset replacement, but still way ahead of the UK. What I'd like to, because you were talking about asset management, and we've been doing that for years here in the centre, and I think the utilities still haven't bought into this idea of the risk-based management of their assets and having asset management systems. So they buy these solutions from SEAMS, from ICS consultants, from Copper Leaf in Canada, and they all believe by doing that they're going to have a good system. And you just said about the data, you put rubbish in, rubbish out. So for me, the idea of the self-healing network has two extremes. One is to have completely redundant systems, so each and every pipe duplicated. I mean, we can't replace the existing ones. And the other one is do nothing but then have a digital twin that is going to predict or give you an idea that something is going on with you. And that's what I would call a self-healing system, not the one that repairs the pipe. And because look into what telecoms are doing. They're doing the same thing. They don't have a total redundancy. They have more than we have in our networks. And that's the way to sell the idea of the self-healing system. Get the data that you really need to intervene before the customer feels the impact of something going wrong with the network. So that's a different type of philosophy than what others are doing. I'll replace everything.
And I've seen that. I had actually a long conversation with Waternet, with an Amsterdam water company, about their asset management practices and so on as part of some project. And they explained in quite a great level of detail, the rules they are applying. They're not as simple as let's replace every X years. They're quite refined, it depends on a number of parameters and so on, but there are still if-then rules. There are still rules, depending on this, this and this, we will replace this frequently. And there is still reluctancy to go into building any predictive models, anything that we have heard today pretty much in the introductory part, because I don't know what are the reasons. Perhaps these models are not seen as accurate enough, widespread enough for them, or they are just simply reluctant to change their daily practices, In the Netherlands, utilities are publicly owned, unlike here, and they are relatively well funded, and they just keep going on as before. There is really no incentive for them to change much. That's my perception, at least.
That's everywhere. I mean, the regulator is not pushing the UK companies to do anything about it, because they say, oh, we don't want to give you a solution that you take. You have to come up with a solution, and that's the wrong way around. And also, I think what happened in the UK is that early adopters get the hit, because like Southern Water came into, they put smart meters, 95% coverage. That's all technology in 2 years' time. Yeah. So who is going to make that mistake again? No, they're reluctant to do it. And Thames have to do it because of the lack of water resources for the future. So
there is also another view, which I heard again from someone from the UK a long time ago. Early adopters take all the risk as well.
Yeah, but that's what I meant.
Yeah. But then that means that why not just wait, and buy the technology when it is more mature. And that's the thinking behind quite a few people in the industry.
Do you think that the Ofwat Innovation Fund is a step in the right direction? I mean, in that, because obviously at least there's innovation, there isn't necessarily pressure.
It definitely is a step in the right direction, but I think the industry is using it to do business as usual. Although the big criteria in there is that they go beyond the business as usual. I've been on several of those evaluation panels. They fund the center of excellence in the water sector. That's what they funded. They have Aqua, and they fund the new, and it was pushed through politically. I can tell you. Don't repeat this.
But Dragan, I think we can agree that at least as a minimum, this latest initiative is good for the researchers in a sense that the companies are encouraged to share data. Some of the data that I've seen presented today, I tried to get off Southwest Water and other companies for many years and never succeeded really. And I'm really pleased to see that has changed. They are willing to share more, and they are willing to support at least that much.
But it's not just knocking door and getting data. It's several years of trust and working with them.
That was the first bullet point in my presentation,
exactly.
Building that trust with individuals within organizations.
And unfortunately, sometimes those retire,
yes.
And you lose that key contact in the company, and you have to start again from scratch.
Yes, and I know that from personal experience as well, but there were cases where I would develop trust, we would sign the NDA,
and then we would wait for data, and it would never come.
Yeah, maybe Shuming can tell us how things in Beijing.
Well, in the same situation, you trust is the first step. And then when you have the trust, you retires.
He retires. Takes that long.
Normally that's the same situation. Well, actually, I got something when I sit there, because 10 years ago in CWS, if you look at the papers from CWS, normally it's genetic algorithms, optimal typing, this kind of papers. But today, for presentations, or 5 presentations, you got to practice. Generally, there's no genetic algorithms. You have done a lot of experiments. Yes, that is just one part of your tools, and you have done a lot of experiment to get some field data and to support your methodology. I think that's very, very good. Because we are in the age of AI. In AI time, it is very easy to grab a method and just try to train to see what we can get. And we don't know why we get this one, but we know we get something. So when we are talking about data quality, what you say, we tried our best to collect data and try to give it to you. But for scientists, we don't know, the condition behind the data, how they collect the data. We just trust the data. We use the data. We generate something, and the AI, yields something for us. So I think it's very essential. You did some experiment, and you use the experiment to help the AI to learn by itself. So I think this is very, very essential. That's also the reason why I asked she that question. Why do you think cosine distance is the best? You test 1, 2, 3, 4, 5. Okay, number 4 is the best. Maybe number 6, you haven't tried that one. That's the best. We don't know. So we need to know the philosophy. What is the physical meaning of the data? We need to help the AI to understand the data and then to learn by themselves. And that will, make the result acceptable by industry.
I know we're almost there.
Yeah, like final comments
But
from all the panelists, please.
I just wanted to say I fully agree with Shuming. As someone who published papers on AI, I'm seeing actually a worrying trend, and I think AI will end up in machine learning where GA and that will end up. That's my worry, and I see AI and machine learning being thrown at problems where it can help, but also the problems where it's not necessary. Where there are other means, just because that's the kind of fashion latest.
But
No, we are not blaming you.
I was pleased to see your statistical method.
I just want to say that actually as a PhD student that we are struggling to publish papers, but every time when we want to do something real, actually I tried lots of times, usually the simplest one are the most robust one, but it's very hard to publish based on that because reviewers are requiring, well, this is outdated. We want transformers, we want GAN, and that's what we want to see.
I think we have,
Yes,
we have to guard against that, don't we? I think, and if you show that the simpler method is as good or better than the newer ones, I think that's fine. And I'm just going to say, I agree with Shuming as well, and I think we need to, but we also need to collect the data, the features, the granularity, the temporal granularity of the data in such a way that it, with the idea that we're going to use AI as on that data, and that AI is going to have a product that's going to go into a business and be used for a number of years. And I think that's sort of, it's chicken and egg otherwise, isn't it? Because until a company or the companies see the outputs and the benefits that can be drawn from AI applied to data, it's very difficult to encourage the investment in the data collection in the first place, right? So I think the more we can do of that, the more of these projects we can get in and actually working and helping businesses, I think the better.
I mean, talking this, my final thought after Zoran and Ed said about data and about methods, I think we should move away from method-based or method-centric approach to data-centric approach. So in the past we were looking, which new neural network or whatever is going to be better for our data, but we should actually focus more on the data and see First, how do you divide the data sets into training and testing and validation? Do you have the same distribution? You know, like the classical stuff. What can you do by visualizing data? What can you do to repair the data set, infill the data set, put the historical, and then, you know, the modern methods are deep learning and whatever they're called these days are so powerful, and you apply 3 or 4 of them and there isn't much difference. So I think we need to look more into the data set, and that has to be the future approach.
Thank you. Any final comments from the panel? If not, thank you very much. Thank you also to all the speakers. Just a reminder, there is a poster presentation session at 1:30. Could you please, after you grab some food, if you are interested in any of those 3 poster presentation sessions, please at 1:30 go to one of the stations, and the students are going to do 1-minute presentation about their poster.
Or is it going to rotate, or if
No,
you
just
choose one, you'll have
one
okay.
presentation, and then we'll have additional half an hour after present. If you like to see other posters, please feel free to go to others.